It's been 1 year of observations from the James Webb Space Telescope, and what a year it has been. There have been so many interesting observations, discoveries, and pictures of nebulae, galaxies, clusters, images inside the solar system, newly forming planets, and fascinating chemicals detected in the atmospheres of planets around other worlds. And this is just the first year. Some of the observations were kind of what we were expecting to see, and others were complete surprises, things that are going to reverberate through cosmology for years to come. With this episode, we're going to give you a comprehensive look back at what happened in the first year of observations with JWST. We'll cover all the great pictures, the interesting science results, the new discoveries, the things that make you scratch your head and go, what? And some of the problems that the telescope experienced. We'll also look at what the future holds for year 2. If you were really excited about the launch of JWST, but then didn't catch too many of the big stories that broke over the course of the year, this is a chance for you to completely catch up. You'll be able to talk with your friends and understand all of the science that was made over the course of the year. If you just want a reminder, if you want to just have some nostalgia about some of the amazing discoveries and the really cool pictures that we saw this year, this video is for you. So, let's start with the pictures. The first picture that I want to look at is of the Tarantula Nebula. This has got to be one of the best pictures taken all year. The Tarantula Nebula is one of the largest star-forming regions that astronomers have ever found. It's located in the Large Magellanic Cloud, which is a few 100,000 light-years away from Earth. So, it's not even inside our galaxy. It's in a completely separate galaxy. And yet, it is so big. There are so many stars forming, many of which are dozens of times the mass of the Sun. You're going to hear me say this a bunch of times, and that is that JWST is equipped with a range of infrared instruments. Infrared is this wavelength of light that allows you to see through the gas and dust that normally obscures places like star-forming regions. Under the Hubble Space Telescope, you might just see this blob of dust, but with James Webb, you can peer through the dust and actually see the stars as they're forming inside these cocoons of nebula. In this picture of the Tarantula Nebula, you can see all of these knots and regions where new stars are forming. You can see through the gas and dust to some of these protostars as they're blasting out radiation that is pushing away the nebula material and exposing the stars. Over time, these giant cavities of dust will just get bigger and bigger, revealing all of the stars. This is one of those pictures you can go and dig up the full-resolution image, and it measures 14,000 pixels by 8,000 pixels across. This was one of the first pictures that was taken by JWST. It's just that the astronomers decided to release the image of the Carina Nebula first and hold on to this one until later. While the Tarantula Nebula is probably the most significant star-forming region that we know of, the Orion Nebula is probably the most famous. So, it was inevitable that astronomers would turn JWST onto the Orion Nebula. The Orion Nebula is a familiar object in the night sky. If you've got dark skies, you can actually see it in the sky with your own eyes, but you can definitely see it in binoculars or a small telescope. This picture is of a region called the Orion Bar, and you can actually compare this image taken by Webb with one taken by the Hubble Space Telescope. You see these bright stars and how they line up, and then when you see that comparison, it really gives you a sense of how good the optics are on JWST versus the optics on Hubble. All of the major structures are there. It's just like they're in better focus. That is the power of a 6.5-meter mirror compared to Hubble's 2.5-meter mirror. One of the coolest pictures that came out this year is of a Wolf-Rayet star, WR140. Wolf-Rayet stars are newly forming stars that are incredibly hot, putting out an enormous amount of radiation. When astronomers looked at this original image of the star, they noticed these bizarre concentric rings. This isn't an artifact in the image. This is real. There are actually these rings in the nebula material around this star. What's going on? The star has a binary companion, and the star is blasting out this nebula material into this cloud around it. This stellar companion is moving through this material and carving out rings as it goes. You get this ring after ring after ring. It's kind of like measuring the tree rings to figure out how old a tree is, but in this case, you know that this binary companion flies past the star every 8 years. Each one of these rings matches 8 years of time of stellar evolution for this young star. The most iconic picture taken by the Hubble Space Telescope has got to be the Pillars of Creation. This is another star-forming region, and in this case, you're looking at the Eagle Nebula, which you can see in a small telescope. In fact, With a small telescope, if you've got a camera attached, you can actually take pictures of the pillars of creation, but nothing like this. I mentioned earlier about the Tarantula Nebula and how these stars create these really powerful stellar winds. These stellar winds can shape the structure of the nebula around it. The pillars of creation are these places where, at the very top, you've got this newly forming star that is surrounded by this envelope of gas and dust. The collective power of all the other stars in the nebula is blasting away, like wind, sand blasting this material away. It forms a comet-like tail, a column, leading away from the star. Astronomers think that these pillars, as we see them today, have already collapsed due to the powerful stellar winds. It's just going to take us a few thousand years to see a newer version of it. With the original Hubble version, you got this wonderful picture. Then James Webb comes along and takes an even higher resolution picture that also sees through some of the gas and dust that's obscured by the Hubble Space Telescope. You see higher resolution, but you also have almost X-ray vision to see into these star-forming regions. James Webb is equipped with multiple instruments that are good at different things. In the first picture, this was taken using NIRCam, the near-infrared camera. In the second picture, you're looking at the image using the mid-infrared instrument, MIRI. It's a different wavelength of infrared light. With MIRI, you get all of the gas and dust surrounding the stars, but the stars themselves disappear because they're no longer covered in the gas and dust, and they just don't appear bright in the mid-infrared. Different wavelengths of light, as they come into Webb, reveal different parts of the nebula. Astronomers are able to use this to learn a lot more about what's going on in the star-forming region. James Webb has been turned on newly forming stars that aren't surrounded by clouds of gas and dust. In this case, you're looking at a protostar designated as a Class 0 protostar. This means that the star is only about 100,000 years old and is located about 430 light-years away from Earth. The star is surrounded by an accretion disk, a disk of material that's being pulled into the star to add to its size. It's in there where we would expect to see planets starting to form around the star. The magnetic field lines are whipping out this material along the poles of the star, blasting off into space. If you could go back in time and look at the sun as it was forming in the solar nebula, this is the kind of thing you might see just a few 100,000 years after the solar system started to form. We've seen a lot of galaxies with James Webb, and when you see these pictures, they're instantly recognizable. I call this the Eldritch Horror version of astrophotography because the colors are these dark purples and salmon colors. They make you think of some kind of gothic horror. Huge props to Judy Schmidt, an imaging specialist, who pioneered a lot of the early work with the images coming from the James Webb Space Telescope. Before the astronomers and the visualization specialists working from space agencies and universities, Judy was in there looking at the data as it was coming off of the telescope and putting together images that we could see. The colors are very recognizable because the regions of a galaxy that light up in the infrared spectrum are once again these areas of gas and dust. Less of the bright older stars and more of the regions where these stars are forming. Often, stars form in the galactic arms of their galaxy. The images from James Webb really show off where the arms in the galaxy are, where the star formation is happening, and where we can expect to see future star-forming regions. It's like the skeleton of a galaxy. Not only is James Webb a powerful telescope, but when it lines up with a gravitational lens, it becomes an incredibly powerful telescope. You're using the gravity of an entire cluster of galaxies as a natural telescope lens. With that, you can observe objects on the other side of the lens with more precision to see what kinds of elements are in these distant galaxies that you just wouldn't be able to see with the capability of the telescope itself. You get some other advantages as well. In this case, James Webb was able to see multiple versions of the same supernova going off in a galaxy because the light has to follow a different path around this gravitational lens, around this cluster. Astronomers were able to see a Type 1a supernova go off in a galaxy that was lensed by a galaxy cluster. They were able to see it go off multiple times, depending on the length of the journey that the light had to take to go around the galaxy. This is just amazing. It's not a James Webb thing, but just the fact that you can use the gravity of a galaxy cluster as a natural telescope to see objects tens of thousands of times better than you can with just your telescope alone. We don't know what dark matter is, but we can use it as a telescope. This picture will look instantly recognizable as a James Webb picture because you see that six-sided star. Of course, That's coming from the hexagonal shape of the mirrors that give all of the bright objects and images from Webb this very distinct six-pointed star image. If you look very closely, there are actually two additional lines that come from the struts that hold out the secondary mirror on James Webb. This is an object known as ARP-220, which is two galaxies crashing into each other. The resulting merger is so bright that it is starting to overwhelm the sensors on JWST. We've seen this picture in visible light, and it's fine. Pretty cool to see two galaxies coming together. But because you've got all this gas and dust mashing together, it's incredibly bright in the infrared. It's shining with the light of 1 trillion suns, about 100 times brighter than the Milky Way would look. This is the first step to the sort of long decline of the giant galaxies. Eventually, this will turn into one of these giant elliptical galaxies. Think about galaxies like M87. They are the result of all of these giant galactic collisions that have sucked up all of the smaller dwarf galaxies and larger galaxies in their region. There's nothing left to eat, and then they just settle down, forming a giant ball of stars and fading away into redder and redder stars over time. The picture that NASA chose to celebrate the first year of James Webb observations was this picture called Rho Ophiuchi. This is the Rho Ophiuchi star-forming region. It's located less than 400 light-years away from Earth, and it is the closest star-forming region to Earth. We've had the biggest, the best-known, the one that was made iconic by Hubble, and now we've got the closest star-forming region. It's a very small star-forming region. There's only one star that is the size of the Sun or larger, and it's the one that dominates the lower left of this image. The rest are smaller and will probably turn into red dwarfs over time. Thanks again to the infrared view, we can see through all of that gas and dust and see the star underneath. One of the things I really love about Rho Ophiuchi is that this is an image you can take a picture of with a small telescope, or if you've got a digital camera and a good tripod. During the summer, when the Milky Way is overhead, you can take a picture and see this incredible region in the Milky Way. It's such a great object. All right, we've looked at all the pretty pictures. There's lots more pretty pictures to come, but let's really talk about the science. Let's look at the scientific capability that Webb was designed to fill, and this is to use its infrared instruments to look back to the beginning of the universe, the time when all of the building blocks of the modern galaxies that we see today were all coming together. This is because the universe has been expanding over time, and the light that's been coming from different objects has been redshifted. Even though it may have started out in the ultraviolet or in the visible light spectrum, over the billions and billions of years of the expansion of the universe, the light has become more and more redshifted. Things that were in the visible light 13 billion years ago are now in the infrared today. Requires an infrared instrument to be able to see that far back in time to that great distance. The big expectation was that James Webb would allow us to see the earliest galaxies ever seen, the ones as they looked just a few 100 million years after the Big Bang. The Hubble Space Telescope had already taken our view back to, in some cases, really just about 1 billion, less than 1 billion years after the Big Bang. It was expected that James Webb, with its increased power and capability, could take that further, and it did. Within a few weeks of Webb coming online, we saw paper after paper with people claiming to have seen the farthest galaxy, the galaxy that formed the earliest after the Big Bang. We saw numbers like 300 million years after the Big Bang, 200 million years after the Big Bang, maybe sooner. But then you had a whole series of other papers taking a really careful look at the research being done. At this point, the consensus is that the galaxies are seen between 300 and 400 million years after the Big Bang. The techniques have improved, and now you can expect that every couple of months we're going to see a slightly more distant galaxy. This is because Webb is doing these enormous surveys of the distant galaxy. With the Hubble Space Telescope, we had the Deep Field Survey where they stared at a seemingly empty spot in the sky, observed for hours and hours, days and days, and were able to see that it was actually filled with hundreds of thousands of galaxies. Webb is doing the same thing, but Webb is vastly more powerful. Webb doesn't have to take breaks. Webb is doing a survey and should turn up millions of galaxies in a very tiny spot in the sky. Some of these are going to be farther and earlier than anyone's ever seen. Over the coming years, anticipate seeing this record get broken over and over again. Who knows where it's going to end, but the most distant objects will probably be seen using gravitational lensing. This technique uses the power of a foreground galaxy cluster to observe some object that wouldn't otherwise be revealed. More importantly, with that gravitational lens, you can see the chemistry of this distant galaxy and understand what it's made of. What was more surprising was the size and scale of the galaxies being seen. In some cases, Webb was seeing galaxies that were as massive or more massive than the Milky Way. The Milky Way has been around for the entire age of the universe. It took billions of years to pull together all of the dwarf galaxies and assemble this large mature spiral galaxy. Yet Webb is seeing galaxies like the Milky Way early on in the universe. This is one of the first major controversies coming from James Webb, that the early galaxies were too big, too early. If the galaxies truly were as massive as we're seeing them, then some of the underlying assumptions in cosmology, some of the models for how the universe came together, are incorrect. But astronomers have had the time to look back through the models and the observations. Although exciting, these findings don't necessarily break the widely recognized models of how the universe formed, such as the ratios of dark matter to dark energy and how smaller dwarf galaxies came together to form the larger structures. One of the most exciting surveys that JWST is doing is called the JADE Survey, JWST Advanced Deep Extragalactic Survey. This is Webb's version of the Hubble Deep Field, staring at one region with many hours assigned to Webb over the course of that first observing year. Many more hours are planned for the next cycle, which we'll get to later on in the episode. Already, Webb is seeing 10 times as many galaxies in the same region of space with 15 times the detail that the Hubble Space Telescope saw. One of the most important tools that astronomers use to understand the chemistry of stars is called spectroscopy. This is where they take the light of a distant object, a star, a planet, whatever, and break it up into a rainbow. Then they look for very specific lines along this rainbow called absorption lines. Those absorption lines tell you the chemistry of what's in that star, what's in that galaxy. One of the most surprising findings is that Webb detected the presence of organic molecules seen early on. Another example where astronomers had to use gravitational lensing to see it, but they detected what are called polycyclic aromatic hydrocarbons. This is a byproduct of combustion. If you have a fireplace, you know the soot in your chimney, that's the same stuff. They're finding it in a galaxy that is billions of light years away, early on in the universe. This is really exciting because the earlier we see organic molecules in the universe, these are the building blocks of life and could help explain how complex organisms like we have here on Earth might have formed in the universe. Not only do we see the most distant galaxies, but we see the most distant quasar. A quasar is a supermassive black hole that is actively feeding on material, so much material that it can outshine the rest of the galaxy. The most active time in the universe is known as cosmic noon. This is a couple of billion years after the Big Bang when the star-forming regions in these galaxies were actively forming new stars and planets. The supermassive black holes at the hearts of these galaxies were siphoning in material from the galaxy around it, shining these bright quasar lights out into the universe. Once again, it looks like the universe was able to get into this activity a lot earlier than anyone was expecting. So we saw this. Quasar called Sears 1019 contains about 9 million times the mass of the Sun, roughly twice the mass of the supermassive black hole at the heart of the Milky Way. We're seeing it just 570 million years after the Big Bang. Jacob saw other supermassive black holes a few 100 million years later, some of which had already gained 1 billion times the mass of the Sun or more. How did these black holes pull together so much material so quickly in the universe? When you zoom out, you see the cosmic web, the large-scale structure of the universe where galaxies and galaxy clusters pull together into giant structures. Astronomers describe these walls and filaments with large voids in between, as mutual gravity pulls galaxies together and opens up giant spaces in between. With James Webb, we go back to the earliest moments in the universe and see the initial stages of this large-scale structure forming. It's just a handful of galaxies, but a massive galaxy acts like an anchor, using its gravity to pull in smaller galaxies into a long, thin filament of galaxies about 3 million light-years long. This is seen just 830 million years after the Big Bang. The other big job for James Webb is to observe exoplanets, both newly forming and mature ones around other stars. Thanks to its infrared capabilities, the telescope can see through the gas and dust of star-forming regions to view planets as they form around newly forming stars. It allows astronomers to measure the chemicals in the atmosphere of a planet separate from those in the star it orbits. Astronomers point James Webb at a star where they know a planet will pass directly in front of it, taking images of the star itself. As the planet passes in front, the presence of its atmosphere can be detected, and from that, the chemical fingerprint of the atmosphere can be determined. One image, WASP-39b, located about 700 light-years away, is a hot Jupiter, definitely not a habitable world. Yet Webb picked up a clear, unambiguous signal of carbon dioxide in its atmosphere, the first time carbon dioxide had ever been seen in another planet. It also detected water vapor, potassium, sodium, carbon monoxide, and other chemicals in the atmosphere, many for the first time on another planet. The most exciting worlds we're all waiting to see are the TRAPPIST-1 system, a red dwarf star orbited by 7 Earth-sized worlds, several in the habitable zone. If there's any place that could have life, this is probably it. Webb is examining these worlds one by one. So far, 2 planets, TRAPPIST-1b and TRAPPIST-1c, have been analyzed. TRAPPIST-1b, like a super Mercury, has no atmosphere. TRAPPIST-1c, hoped to be like a super Venus, also has no atmosphere. There are still 5 more to examine, with those in the habitable zone up next. In the world of exoplanets, we often don't get pictures but rather spectral data, knowing the chemistry, orbital period, radius, and mass of the planet without a visual image. However, if conditions are right, a direct image can be taken. This has been done from the ground many times, but Webb took its first direct image of an exoplanet, which has 9 times the mass of Jupiter and orbits an A-type star far from its star, at 92 Australian dollars. The star is so bright and the planet large and far enough away that Webb distinguished between the star and its planet, providing a picture. Webb also confirmed an exoplanet found by NASA's Transiting Exoplanet Survey satellite, TESS. TESS detected a candidate planet, and follow-up observations with Webb confirmed it. The planet is Earth-sized, but we don't yet know if it has an atmosphere, potentially making it a future target for Webb to characterize. Beyond planets, Webb has been observing brown dwarfs, which are considered failed stars, giant Jupiters somewhere between a red dwarf star and a giant planet. Because they are cool, they are perfect objects for Webb's infrared instruments. Webb looked at a triple brown dwarf system and detected silicate in the atmosphere of one, along with methane, carbon dioxide, carbon monoxide, sodium, potassium, and water vapor, providing clear signals for the presence of these chemicals. Many exoplanets found so far are hot Jupiters, stars with several times the mass of Jupiter that orbit incredibly close to their star. They are relatively easy to find due to their large gravitational influence on their star and the significant amount of light they block when passing in front of the star. One of the most famous is WASP-18b, known since 2009, which takes just 23 hours to orbit its star. With 10 times the mass of Jupiter, Webb made a temperature map of WASP-18b's atmosphere, showing it is tidally locked to its star. The day side is 1,000 degrees hotter than the night side, indicating poor heat distribution from the day side to the night side. James Webb has also spent time observing targets within the solar system, looking at all the planets it can: Mars, Jupiter, Saturn, Uranus, and Neptune. It can't look at Earth, Venus, Mercury, or the Moon due to the sun shield protecting its instruments from the sun's heat and Earth's glare. For Mars, Webb took infrared images showing different kinds of rock on the surface. For Jupiter, Webb provided stunning images with visible atmospheric bands, the Great Red Spot, and polar hazes. Saturn's image revealed its bright rings and dim, murky atmosphere. Uranus's face-on rings, composed of dust, showed large chunks up to 20 meters across, with several moons visible. Neptune's rings, dusty and seen since Voyager's flyby in 1989, showed upper atmosphere features and moons, with Triton bright and visible. Webb's annual images of these planets will allow astronomers to track surface changes, storm growth, and seasonal effects on their atmospheres over time, providing a better understanding of how these planets change year by year. Webb also imaged moons like Enceladus, known for its geysers spraying water ice into space. Webb detected these geysers from a distance, measuring plumes extending about 10,000 kilometers and ejecting 300 liters of water per second, enough to fill an Olympic swimming pool in a couple of hours. Webb hopes to see other molecules detected by Cassini, like hydrogen gas and organic molecules, but wasn't able to in this set of observations. But we'll see over time with more observations year after year. We may get those more sensitive signals starting to come out of this data. We got images of Titan taken by the James Webb Space Telescope. Titan is Saturn's largest moon and a moon with a very thick atmosphere where it rains methane. There are methane lakes on the surface, mountains made of ice, and Titan seems to have organic molecules on its surface. Even though the Cassini spacecraft was at Saturn, it doesn't have the same kind of optics and infrared capabilities that the James Webb Space Telescope does. These images coming from James Webb are able to see through the haze surrounding Titan and reveal some of the surface structures. You can see some of the northern region called the Kraken Mare. With continued observations from James Webb, we'll get a much better idea of the geologic features on the surface of Titan. This is perfect because NASA is sending a nuclear-powered helicopter to the surface of Titan in the next decade, and now we'll know where to look. When asteroids pass in front of stars, you get this perfect opportunity to learn more about the asteroid itself. In this case, James Webb was able to participate in an occultation of the asteroid called Chariklo. Astronomers know that this asteroid has rings. As the asteroid passed in front of the star, Webb was able to make really accurate measurements of the rings to watch the dips in brightness as each one of the rings passed in front of the star. Last year, we also had the DART mission, the Double Asteroid Redirection Test, where a spacecraft was slammed into asteroid Dimorphos, which is a moon of Didymos. Astronomers around the world and space telescopes turned to watch the aftermath of this epic collision, and Webb was able to see this expanding cloud of debris coming from asteroid Dimorphos from this amazing impact. Afterwards, astronomers were able to measure exactly how much of a change in the orbital velocity of Dimorphos around the larger asteroid occurred. It's been an incredible year of science observations, but Webb wasn't without its problems. The first big problem was that the space telescope was hit by micrometeorites. This was expected as there are tiny bits of dust in the solar system that are expected to crash into the mirror and slowly degrade the optical capability of the telescope. However, in May, a fairly sizable piece of dust crashed into the telescope, causing a noticeable amount of damage. Still, the capabilities of the telescope are fine and well beyond the expectations of the astronomers. Based on this damage, the team working with James Webb decided to change the way the telescope makes its orbit. Before, it would turn in all directions it was capable of seeing to look at whatever targets it needed to, but now they decided to do most of their observations downstream, behind the telescope, as it orbits. This way, the added velocity of the telescope and any piece of dust it crashes into would be minimized, reducing potential damage to the optics. There was also a problem with Webb's MIRI instrument, the mid-infrared instrument. MIRI has 4 modes of observation, one of which is the medium-resolution spectroscopy mode. Engineers detected excessive friction in this mode, so they shut it down to use the rest of the modes and diagnose the problem. After a couple of weeks, they were able to bring it back online. Another issue arose with the near-infrared imager and slitless spectrograph, but it wasn't with the instrument itself. They had a communication delay problem sending data to and from the instrument. This object is important for studying exoplanet atmospheres and distant galaxies. They had to bring this instrument offline, debug the communication delay, and then put it back online. As of now, every part of Webb is working perfectly. Such problems are natural for all missions, and scientists work to repair instruments, bring modes back online, debug software, install patches, and keep the telescope running. There's no part of Webb that you should be concerned about at this point. The telescope is working above and beyond the original expectations, producing amazing science. What's next? This wraps up 1 year of James Webb observations, and it has been a very busy year. This is just a fraction of all the observations Webb made. Much of the time on the telescope was awarded to individual astronomers who are writing up their research papers, and they have a 1-year embargo for their data. After a year, that data is released to the public, allowing anyone to look through the older data, make discoveries, and write their own papers based on what they find. The first year included a lot of this embargoed data, but ongoing discoveries will continue as more data is released. There is some debate about the data release system. On one hand, a 1-year embargo allows astronomers to take the time to do a proper study, release results into a peer-reviewed journal, and have other astronomers review it. On the other hand, if the data were released to everyone immediately, it might lead to a rush, and the first person to publish might get the most publicity without necessarily producing the best science. This process helps to ensure good science, but might slow down potential discoveries. All observations made last year were part of Cycle 1, determined by the Space Telescope Science Institute, which manages the day-to-day operations of Webb and Hubble. Recently, the announcement of Cycle 2 outlined all the observations Webb will make in its second year of operations. Once again, there are many exciting targets Webb will look at, and we will report on its findings over the upcoming year. 1 year of observations from James Webb revealed a lot of exciting discoveries, and the telescope is doing great. It was launched into a very precise orbit, which will likely extend its operational life much longer than expected. Originally, astronomers hoped for at least 10 years of operation, but now it looks like the telescope could last 20 to 25 years. Hopefully, I will get a chance to do this 25 more times as we continue to learn more about the universe. This is just the tip of the iceberg of all the work done with the James Webb Space Telescope. I write a newsletter every week, giving a high-level overview of all the interesting stories in space and astronomy. We cover all these stories in Space Bites every week on the channel, write full-length articles on the Universe Today website, and I do interviews with many of the scientists behind these discoveries. We'll have links in the show notes to many of the interviews that went along with this episode. I enjoyed this special, very long episode discussing all the great discoveries made by James Webb. I'd love to know what your favorite picture or story was this year. Just put a note in the comments and let me know what your favorite research done by James Webb was in its first year.